let's solve number 12 next. Here we have to prove that a local ring contains no idempotent, that means no idempotent element other than 0 and 1. So we start the solution by considering a local ring. Let A be a local ring with maximal ideal M. Let's recall that a local ring is a ring in which there is exactly one maximal ideal. So this is that maximal ideal. And then let E in A be an idempotent, that means an idempotent element. And let's also recall what an idempotent element is. It's an element whose square is equal to the element itself. Now this is what we consider E times E minus 1, which of course by the distributive law is E squared minus E. Now you apply the fact that E is idempotent, so E squared will be equal to E. So that's how this becomes 0. Now we consider two cases depending on whether E is a unit or it's not a unit. If E is a unit, then Fe is equal to 1 for some element F in A, the multiplicative inverse of E. But then let's consider E minus 1. E minus 1 is of course equal to 1 times E minus 1, and in place of this 1 you can write Fe. And then you have already found that E times E minus 1 is 0. So I should have written one more line, but you understand that here we will have F0, F times 0, which is equal to 0. Note one more thing, that I have not really cared much about separately bracketing Fe and then writing one more line where we will have F times E minus 1. I am not doing that because it's understood that multiplication is associative. So this product is well defined even without using further parentheses. So we are now getting the fact that E minus 1 is equal to 0. So from that we get E equal to 1. So in this case, if our idempotent is a unit, then it has to be equal to 1. And next we are going to consider the other case where it's not a unit. If E is not a unit, then E has to belong to M, that lone maximal ideal. Why? That is because of corollary 1.5. You go back and see the statement of corollary 1.5. It says that in a ring, if you have a non-unit element, then it must be contained in some maximal ideal. Because the only maximal ideal available to us now is M, so E now needs to be inside M. Alright, and next we again consider the fact that E is maximal, and that is why it's a proper ideal. By definition, it's not equal to the entire ring. So E being an element of M and M being a proper ideal prevents E minus 1 to also be inside M. What would happen if E minus 1 is also inside M? Then their difference, that is 1 will be inside M, but if 1 is in M, M is forced to be equal to the entire ring, which it is not. That is why E minus 1 cannot belong to M. But then again, this implies that E minus 1 is a unit. Why? Again by corollary 1.5. Because if E minus 1 is not a unit, then it has to be inside a maximal ideal, but the only maximal ideal is M. So this fact implies that this now has to be a unit. And because of that, E minus 1 times G is equal to 1 for some element G in A, which is the multiplicative inverse of E minus 1. But then let's consider the element E alone. In place of E, we can of course write E1, E times 1. And in place of 1, we can write E minus 1 times G. And we saw in the beginning of the solution that E times E minus 1 is 0. So that means we are getting 0G, which is equal to 0. So we see that in this second case, this is 0. But in that first case, it was 1. So we find that if you consider any idempotent element in a local ring, it needs to be either 0 or 1. Conversely, of course, we know, and it's a simple thing, that 1 and 0 are idempotent elements. So in a local ring, these are the only two idempotent elements, and that's what we wanted to prove.